try to grab two smaller functions to build a new function. We use function compositions as an example. If we're going to go to, let's say, Kohl's, and we're going to buy something that is on sale. So the first function is the sale price. And then as we're standing in line, we might be able to decide if we can afford it because we need to determine what the sales tax would be. So our first function is the discount function. And once we figure out the discount, then we're applying sales tax to our item. So as an example, if I went to go buy a $20 shirt and it's on sale at 15% off, this means that our shirt is $17, and now we must calculate the shirt will cost after sales tax. Let's just round it to 8%. Your total cost for the shirt after the discount and sales tax will be $18.36. So by grabbing two different functions and combining them together is what we call composite functions or function composition. So I have under there that the price of the shirt after the discount is our f of x function, and the price after the sales tax then is our g function. So what we ended up doing then, the function for the final cost of the shirt is g of f of x. And it can also be written as g of f of x, where we do the innermost function part first. So we took the discount first, and whatever the discount was, we put it into our g function, which was the sales tax. So then the g function was the second piece to the puzzle. Moving over to slide 2 then. Function compositions are two functions, f and g. The composite of g with f, we can denote it as g of f, is defined by this formula. So there's two different ways in which we can write. We can write g of f of x, or we can write it as g of f of x. I'm going to simultaneously work with both of these at the same time so that you understand that they mean the same thing. And what it's telling us is that x has to be an element in the domain of f, and f of x is an element in the domain of g. So I have like a little picture where I have, when we substitute x into our function, it has to be in the domain, but then it also has to be in the domain of g as well, because we're going from one to the next to the next. And if any of you have coded before, function composition is utilized in many coding languages across the board, and it's very important to coding. So in your notes that I had within Blackboard are just plain notes. It's a clickable link if you wanted to read more about how coding utilizes function composition. So let's say we have these three functions. We've got function f, function g, and function h. Let's find the indicated function values. I want to know what is g of f of 1. So this is the same thing then as saying I want to know what is g of f of 1. So I first need to identify what is f of 1. Whatever that result is, we'll put it into the g function. So I'm first going to say, well, what is f of 1? Well, I know that our f function is x squared minus 4x, so we'll substitute 1 in for each of those values. So 1 minus 4 is negative 3. Now that I know what negative 3 is, I can substitute that into my g function. So 2 minus the square root of negative 3 plus 3, or 2 minus 0, or just 2. I can say then that g of f of 1 is 2. So it's like a two-step process. Let's go backwards, or vice versa, and see what if I did f of g of 1. So if I did the g function and then the f function, I'm looking for what is f of g of 1. So first we start on the inside. So I want to know what is my g of 1 equal to. So 2 minus the square root of 1 plus 3 is 2 minus the square root of 4, which would provide me with 0. Now we can substitute 0 in for my f function since we already know what g of 1 is equivalent to. So what is f of 0? Or 0 squared minus 4 times 0, which is 0. So f of g of 1 is equal to 0. So notice that order matters. Just by flip-flopping our g and our f function, we ended up with a different result. So order does matter. We can also use the composition of functions within itself. So as I'm looking at g of 6, I'm looking for g of 6, or what is g of 6 itself? So we'll first start on the inside. What is g of 6? Our g function. So g of 6 is equal to 2 minus the square root of 6 plus 3, or 2 minus the square root of 9. 2 minus 3, so negative 1. Now that I know what g of 6 is, we can now substitute in and go one step further. What is g of negative 1? So the second part. 2 minus the square root of negative 1 plus 3, or 2 minus the square root of 2. Therefore, g of 6 is equal to 2 minus the square root of 2. Notice I'm leaving it in its exact answer. I'm not rounding or doing anything weird. Leaving it exact. All right, let's head over to slide 3. When we're not actually evaluating, I still have the same f, g, and h functions, but I'm going to indicate the composition function using the functions above, and then state the domain of each. It's important that we look at the domain before we actually do the function composition, before we simplify, just like we did in unit or lesson 1.4. Find what the composition is, then look at the domain, and then simplify. Because as we know, when we simplify, there are some important pieces that may be eliminated that are an important part of the function composition itself. So in part D here, we have g of f of x. So I'm just going to rewrite it in the alternative way, if this is helpful for you. So ultimately, I'm looking for what is g of my f of x function. So this time we don't have a value to substitute in. We're substituting the entire function itself. So I want what is g of my f of x function. Well, my f of x function is x squared minus 4x. So I'm going to look at my g function, and everywhere I see x here, we're going to replace it with x squared minus 4x. This will give us 2 minus the square root. Our x is being replaced with x squared minus 4x plus 3. Before we do any simplifying at this point, we want to take a look at our domain before we simplify. We have an issue underneath our radical because we know radicals have to be greater than or equal to 0 underneath the radical. If I were to simplify underneath the radical, we know we could easily just get rid of our parentheses because there's nothing that we're distributing, no negative to distribute, no value to distribute. And we can't actually combine like terms because it is just 3 values underneath. So when I'm looking at the denominator, or underneath the radical, excuse me, I need to make sure that x squared minus 4x plus 3 has to be greater than or equal to 0 because of the radical. I can factor my value here, 2 numbers that multiply to 3 and add to negative 4 are negative 3 and negative 1. So our factored form is x minus 3 and x minus 1. These have to be greater than or equal to 0. I will have x is equal to 3 and x then is equal to positive 1. So how our domain will look then is we're going to need to look, these are our critical values. Going back to the last lesson, we have to create a little table here. Our critical values are 1 and 3. We can be 1 because 1 would give us a 0, and it's okay to have the square root of 0. And 3 would also give us 0, but we know it's okay to have the square root of 0. We have some test values that we need to use. Let's say we use the test value of 0, 2, and 4. When I substitute into our entire piece, oh, I shouldn't say our entire piece. We don't want to say that. When we substitute into the inside the radical, I will have, when I substitute 0 in, I end up with a positive. Since we'll have 0 here, 0 plus 3 is positive. When we substitute 2 in, I'll end up with a negative. And when I substitute 4 in, we have a positive. We need to be greater than or equal to 0, so we're only interested in those places which our graph is greater than or equal to 0. So our domain has to be from negative infinity to positive 1, and from 3 to positive infinity. There's not much we can do to simplify underneath our radical here, outside of removing the parentheses. So this value here represents g of f of x. And then our domain given is negative infinity to positive 1, union 3 to positive infinity. And if I were to go into my graph here, we would see, if I were to expand it a little bit, that our graph certainly is approaching, oops, that's not 1. Our graph is approaching 1 here, and it's going to shoot up, and then it's approaching 2 here. This 2 is also shifting our graph a little bit, so that's why the shifting looks a little different from what our domain is. So we can't simply rely on what the graph looks like all of the time with respect to the domain. We have to look at our functions and think about the domains of each of the functions to help make it work for us. Let's do another example. This time I want to do f of g of x. So last time we did g of f of x, I want f of g of x this time. So I want, what is f of g of x? I want to know, in my f function, I'm going to substitute my g function. My g function is 2 minus the square root of x plus 3. So anytime I see x in my f function, I'm going to substitute whatever my g function is into it. So here and here. This means I will have 2 minus the square root of x plus 3 squared minus 4 times 2 minus the square root of x plus 3. Before I do anything else, I'm going to look at my function, and I'm going to say I have 2 instances where my graph needs to be greater than or equal to 0. They're the same thing underneath, so I just need to look at one of them. I need to make sure that my graph for my domain, that x plus 3 is greater than or equal to 0. So I need to make sure that x is greater than or equal to -3. So my domain has to be from -3 to infinity. And now we can focus on solving and simplifying. I first need to square this left-hand side. So 2 minus the square root of x plus 3 times itself. 2. And then I'll go back and do the next part. I'm just going to focus on this left-hand side for now. So I'll distribute 2, we'll have 4. 2 times negative square root gives me -2 square root x plus 3. The inside will give me another -2 square root of x plus 3. And a negative square root times a negative square root is positive square root of x plus 3. We multiply the insides times itself because I have x plus 3 times x plus 3. Well, this is a unique situation since x plus 3 times itself is x plus 3 squared. So when I take the square root of x plus 3 squared, happy day, the square root and the square cancel one another or undo each other. So I have 4 minus, combining like terms, 4 square roots of x plus 3 plus x plus 3 when we simplified the right-hand side. Now I'm going to add to this the distribution of -4 times 2, or -8, and +4 square roots x plus 3. At this point, we can go ahead and combine like terms. Notice that I have -4 times x plus 3 and +4 times x plus 3. Happy day creates a 0 pair, so they're eliminated. I still have an x value, and I still have 4 plus 3 minus 8, which gives us -1. So this piece here, x minus 1, is the function f of g of x. We know that that would just be a linear line, but notice that our domain prohibits it from being extended far left because we have to be from -3 to positive infinity. So notice within my graph, when I graphed it utilizing Desmos, before I simplified, I started with where we substituted our values before any simplification to help me identify what the domain might be. Again, if I would have just put in x minus 1, you would have thought that the domain is -infinity to positive infinity because a linear line has no restrictions. But that is only after we simplified. So find the domain and then simplify. Let's have another example on slide 5. This time we are going to work at g of h of x. So this is the same as g of h of x. So I'm going to substitute into my g function whatever h is. H is 2x over x plus 1. So when I see my g function, the only place I need to substitute h into is that x portion underneath the radical. This then gives me 2 minus the square root, replacing x with h, 2x over x plus 1 plus 3. All right, before we simplify, we have two things happening here. Two things that are happening. We have a denominator, which we know cannot be 0, and we have an entire radical that has to be greater than 0. Let's start with our denominator. That one's pretty easy to look at. We know that x cannot be -1 with our denominator, as that would result in a 0. We also need to find another critical value for where our entire piece underneath our radical is equal to 0, so that we can make sure that this in itself is greater than or equal to 0. So our x plus 1 is still going to disappear, but now we need to take our 2x plus 3 times x plus 1, so that truly everything is being multiplied by x plus 1 when we eliminate our denominator. So 2x plus 3x plus 3 is still equal to 0. I now have 5x equal to -3 when I subtract 3 over and combine like terms. And when I do -3/5 and turn that into a decimal, we end up with our -6/10 when rounded. We still are going to have -1 as a critical value that is open circled, because it can't still be that. But we could have -3/5 as a closed circle, because if we solve for 0, we end up with -3/5, and that's okay underneath our radical. We still can use -2 as a test value. We could also utilize -4/5 underneath here, since it's in between. And then we could also use 0 here. We're still going to have the same pattern of plus, minus, plus when we substitute in, except now that will slightly change the way in which we write our domain. We're still going to have -1 that is excluded, because that is where our asymptote is, except we will include -3/5, which now matches what we see here. So we can then go ahead and simplify. If I wanted to simplify underneath our radical to combine these, we need a common denominator of x plus 1. I would now have 2 minus 2x over x plus 1 plus 3x plus 3 over x plus 1. And now that we have a common denominator, we can combine like terms. Oops, need some room for the 2. 5x plus 3 over x plus 1. Let's do h of g of x, because we haven't focused on h, the second part of it, h, if you will. So h of g of x, we're going to substitute into our h function the g function. So inside h, wherever we see x, we're going to substitute in 2 minus the square root of x plus 3. So we'll have 2 times 2 minus the square root of x plus 3 over 2 minus the square root of x plus 3 plus 1. We still have two things going on that we need to be concerned about. We need to be concerned about our denominator because we do not want this to be 0 at all. In addition, we also have a radical that we need to ensure is greater than or equal to 0. We know right away that we can say that x has to be greater than or equal to -3 for the radical. But we do have to do a little bit of solving to identify where is it equal to 0 within our denominator. 2 minus the square root of x plus 3 plus 1. Where is this 0 so that we know where to avoid? I could subtract 1 and subtract 2, giving us negative square root of x plus 3 is -3. Divide by the negative. Square both sides so that we can undo the square root. X plus 3 is 9, and then subtract so x is equal to 6. We know that it should not equal 6 though, because it would give us a 0 in the denominator. So when I'm looking at our two conditions here, we can start for our domain. We can start at -infinity. The first value that we are going to run into is -3, but we have a problem here. The value has to be greater than -3, so we don't even get the opportunity to come from -infinity. We actually have to start at -3 itself, because that is the smallest value with which we can be. So when we're beginning at -3, then we can continue until we reach 6. We're going to have to jump over 6 because we know it cannot be 6, and then continue to positive infinity. Now the only thing that we can do when we're solving is distribute. I'm not going to make you rationalize the denominator at all, and then combine like terms in our denominator. So when we simplify h of g of x, we have 4 minus 2 square root x plus 3 over 2 plus 1 is 3 minus the square root of x plus 3. So again, I'm not going to make you rationalize the denominator because it doesn't have any of those directions in my open math, so it'll save us some time. I can see that my domain starts at -3. It's a point that's there. We have an asymptote where we would be 0 in our denominator that we're skipping over so that it matches algebraically for us with what we see. Look at slide 7. Here we want what is h of x. So I want to know what is h of 2x over x plus 1. So wherever I see x here, we're going to replace it with 2x over x plus 1, which seems kind of complicated. We will have 2 times 2x over x plus 1 over 2x over x plus 1 plus 1. We have two pieces that we need to be concerned about. We don't have a radical this time, but we do have two different denominators. We need to know when our denominator and our numerator here will be 0, because we know that can't happen. So we have to make sure that x is not equal to -1. We also need to know where is this entire denominator equal to 0, because we need to know and avoid that location. Also note that this x plus 1 is included with this x plus 1. So we only need to state it one time because they're identical. When I'm looking at 2x over x plus 1, where is this equal to 0? We can subtract 1, so I'll have 2x over x plus 1 is equal to negative 1. Multiplying both sides by x plus 1, I have 2x equals negative x minus 1. Bringing our x over, I'll have 3x equals negative 1, or x is equal to negative 1/3. We don't need to use a table of values at this point because there's only two locations with which our graph cannot be, resulting our graph in a with zeros in our denominators. So when I start with my domain and we begin from negative infinity, the first value that we will approach is negative 1. We're going to skip over negative 1 to negative 1/3, skip over negative 1/3, and then move to positive infinity. Each one of these locations would have a hole in our graph. We'll talk about that in a moment. But then our next portion is to go ahead and simplify the complex piece that we have. So to simplify, I'm going to first distribute here, providing me with 4x over x plus 1 all over. I'm also going to combine these fractions before I go ahead and reverse and multiply. I need a common denominator of x plus 1, and 1 times anything is itself. I will have 2x over x plus 1 plus x plus 1 over x plus 1. I now have 4x over x plus 1 over 3x plus 1 over x plus 1. I can rewrite this as 4x over x plus 1 divided by 3x plus 1 over x plus 1. I know that when I divide, it's the same as reversing and multiplying. You could certainly skip from this step to here if you like, if that makes sense to you. If not, please add in those additional steps that make sense. So I then have, when we take h of x, we end up with 4x over 3x plus 1. In our graph, we know that there is a hole at negative 1. We also know that there is a hole at negative 1/3, but this is going, not a hole, excuse me, an asymptote at negative 1/3 because that was where our denominator was 0, and we know our denominator gives us the asymptotes. So it's kind of very visible there. If we had not found the original domain before we simplified, we would not know that there is an actual hole at negative 1 that's listed there. So that's why it's important to find the domain before we actually simplify. If we were to have simplified and then identified the domain, you would have missed the negative 1 hole. We would have just seen the asymptote at 3x plus 1. Let's move to slide 8. Here we have 3 different sets. We want to know what is h of g of f of x. Well, thankfully, we already found, and we can rewrite this as h of g of f of x. Nope, too many parentheses. Just 2. There we go. But we already found from example D, we already found what g of f of x is. We already found that g of f of x is 2 minus the square root of x squared minus 4x plus 3. We also know what the domain of this is from D as well. So if I now want to find out what is h of all of that, wherever I see x, I'm going to replace it within my h function with our g of f. So in order to complete this, we first want to start with our very inside pieces and then go to the third one. I will have 2 times all that stuff on the inside, 2 minus the square root of x squared minus 4x plus 3 over 2 minus the square root of x squared minus 4x plus 3 plus 1 itself. We already know the domain of the numerator there, that x squared minus 4x plus 3. We're going to use that to build on from example D. What we do need to find is the denominator where this is equal to 0. So where is 2 minus the square root of x squared minus 4x plus 3 plus 1? Where is this equal to 0? I can subtract 3 by subtracting 2, subtract 1. X squared minus 4x plus 3, dividing by -1 so that our x squared minus 4x plus 3 is by itself. Squaring both sides to undo the square root. If I wanted to go ahead and finish solving for this, we would need to subtract 9 to set it equal to 0. We're not able to factor, so we have to use the quadratic formula. So x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Oops. This simplifies to positive 4 plus or minus the square root of 16 plus 24 over 2. 4 plus or minus 4, the square root of 40 over 2. 40 is the same thing as 4 times 10, and I can take the square root of 4. 4 plus or minus 2 square root 10 over 2. Factoring out the common factor of 2, I'll have 2 plus or minus the square root of 10 over 2, which we can then simplify. So we have 2 plus or minus the square root of 10 over 2. Whew. These are our asymptotes because this is where our values in our denominator would be 0. So when I look at my domain from D, our domain from D was negative infinity to positive 1. And then from 3 to positive infinity. So we're going to build from here, adding in our asymptotes that we found with 2 plus square root 10 and 2 minus square root 10. Well, 2 minus square root 10 would be in between the interval between negative infinity and 1. And 2 plus square root 10 would be in the interval between 3 included and infinity. So building from where we left off, from what we know about the numerator's domain, we will then add in our two asymptotes because that is where our denominator in the fraction would be 0, providing us with our asymptotes. So I'm going to erase some of this down here or up here that we've already worked on so that we can build our domain a little bit more cleanly. Our domain then will be from negative infinity to 2 minus the square root of 10 excluded because it's an asymptote, from 2 minus square root 10 until we reach 1. Skip over because now we're at this location from 3, pick up where we left off, to 2 plus square root 10. Here's our second asymptote. And then 2 plus square root 10 to infinity. So pretty long domain. There's not a whole lot we can do to simplify what we've got. We can distribute the 2 here and here, and then we can combine like terms. So when I find h of g of f of x, we are equal to 4 minus 2 square root x squared minus 4x plus 3 over 3 minus the square root of x squared minus 4x plus 3. You do not need to rationalize the denominator at all. You can keep it as is. There's not much, again, to simplify. We can see the happenings here. We can see where our asymptotes of 2 plus and minus the square root of 10 are located. We can also see that we do go to 1 and where we are at 3, and these points are included, but we skipped in between those two pieces so that the picture certainly does match our domain that we found algebraically. And our last example is if we are given a function composition, what are the two functions that make this composition? So this can be difficult because there are so many choices that you can use to substitute in. So because I choose one, you could certainly see something else and it would also be correct. So just keep that in mind. Ideally, what we're doing in this first one is we want to find our composition such that when we have f of g of x, we get the absolute value of 3x plus 1. So I'm going to let f of x be the absolute value of x itself, and I'm going to let g of x equal 3x minus 1. So when I'm looking for f of g of x, our g of x function is 3x minus 1, I'm going to substitute 3x minus 1 wherever I see x, and that will give me the absolute value of 3x minus 1, which is what we were looking for. So my f function and my g function are the two functions that when I put the composition function together provided me with the absolute value of 3x minus 1. This is one of many solutions that would work in this situation. So just note that there's not a one size fits all. When I'm looking at big G of x is equal to 2 over x squared minus 1. Again, what is f of g of x combined together, which will give me 2 over x squared plus 1. I'm going to let f of x be 2 over x, and I'm going to let g of x be equal to x squared minus 1. So when I find f of g of x, I'm looking for what is f of my g of x function. So wherever I see x in my f function, I will replace it with x squared minus 1. And we get back where we started. Again, this is just one example that would work in this situation of many. H of x, we have square root x plus 1 over square root x minus 1. I'm going to let, we're looking for f of g of x that would work in this situation. I'm going to do something a little different. I'm going to let f of x be x plus 1 over x minus 1. And then I'm going to let g of x be the square root of x. So when I'm looking for f of g of x, I'm going to substitute into my f function my g function, which is f of, or a square root of x. So everywhere I see x, I will replace it with the square root of x. Square root x plus 1, square root x minus 1. Again, one of many results that could give us our h of x or f of g of x. So sometimes you have to be a little creative with how it works. But this concludes function composition for today.